Hello everyone. So this is group 7 and the title of our project is the optimization of ACS based machine. Now my co-team mentor is Professor Meyer. Now sponsoring company TWC Caltech. My teammates are Sam Secret, myself, and Paranjit. So a brief introduction. Our company is TWC Caltech, Caltech Dextron. It's a company that specializes in production of camshaft, crankshaft. The company was founded in 1908, and the major equipment was historically. So the ACS closing machine is responsible for aligning the cope and the drag mode, as in the video, cope, one that goes on top and the drag goes below. And the system comprises of a lift, cope arms, elevator, and a pusher. So the problem faced with the machine is the misalignments of the cope modes. And the goal was to improve the alignment by replacing the hydraulic systems with something more controllable, something more efficient, which would overall increase the quality of the machine. Then our decision matrix was based off showing the image, the alignment, avoiding residuals, maintenance, control. Then the order came out to be the lift frame first, the elevator, the pusher, co-parts, which is the list. Does not involve any design improvements because it doesn't affect the overall productivity of the machine. Then our constraints for design were the space for the lift, the pusher, and the elevator. And also the weight of the lift frame, the elevator, pusher, and the co-parts were constrained. And then our project was assigned a budget of $50,000. Then lastly, the technology constraint was all equipment had to be compatible with that. So our current system comprises of an elevator, as shown in the image, cope and drag mode, lift frame, a closing machine frame, a basement debris ramp, pusher plate, and elevator support frame. And here's a video that shows our current system, which is controlled by hydraulics. Then our design was based off the order of the cylinder selection, the lift frame design, the elevator design, pusher design, simulations, system controls, and maintenance recommendations. For our cylinder details, all cylinders had to be driven by a box screw, and each cylinder had a continuous force of 2,950 pounds, maximum speed of 7.9 inches per second, maximum stroke length of 18 inches, and weight of 101 pounds.
So the first area of focus for the design was the lift frame. Compared to the elevator and pusher, the lift frame has the most available space because there's room on top of the closing machine frame and on top of the lift frame itself. And there are multiple design variations based off of what the sponsoring company decides to select. The designs are based off of the ease of installation, fabrication, and maintenance. The first variation has 4 cylinders on the top of the closing machine frame shown here. There are 2 mounting structures, the mounting plate and offset block. The mounting plate utilizes several bolt connections to the cylinder itself and has an additional face on the bottom to provide additional support that doesn't rely solely on the bolts. The offset block is used to properly line up the cylinders from the closing machine frame to the tabs on the lift frame that are already there. The cylinder rod ends will extend through a modified version of the lift frame where we can drill holes, and then they are bolted on the other side. The second variation is very similar to the first one, except there is an additional support block here on the inside of the closing machine frame to provide additional support for the cylinders, and the mounting plate reflects that change here. The third variation uses a different method of connection to the lift frame. The manufacturer of the cylinders provides a rod end attachment shown here that can be screwed onto the cylinders, and then that will have an additional mounting base shown here. That modification will provide additional surface area connections between the lift frame and the cylinders, which will mean over time it will wear out less in this area because it's not pushing and pulling on that tab. The fourth design variation is similar to the third one, except instead of having the base, it's just a threaded rod that connects right here to the lift frame. That's a very small surface area, so this rod will wear out more quickly than the clevis base over time, and that will need to be replaced more. Here you can see the designs between each of the cylinder mount variations. The next area of design was the elevator. As you can see from this one, there is a lot of guide rails and dirt in the area, so there's a lot less space available. Underneath the elevator, there is a basement area, and there's another support frame shown here and a ramp. That provided a space constraint because the elevator and support frame are very close to each other, so these cylinders on this side were very close in the tolerance on that area. So as you can see here, we had to move the components in a very creative way to make sure nothing interfered with the features currently in place. So the configuration is very puzzle-like when it's all together. The plates here for the cylinders are similar to the lift frame ones, except the cylinders are mounted in the opposite direction so we can fully support the bottoms of the cylinders in the elevator area. And there's a base plate here that attaches to the elevator, and it gets welded on there, and the cylinder rod ends are threaded through and bolted.
Next system designer is for the pressure system. It has external limitations. It fits outside of the lift frame and has a stroke length of about 5 feet or 60 inches, which is why we can't use the cylinders that we use in the lift frame. It has 18 inches max stroke. So for that, we need multiple systems such as rack and pinion, and along with that, we need a motor compatible with the rack and pinion system. For the overall design, it's currently a skeleton design right now because it will need an inverter and a closure for the motor, partial environment, the residuals in the air, and for the overall as well, it will need a closure. Generally, it will be a rack and pinion system that has face plates attached to the open drag and motor at 5.5 HP minimum. We chose 7.5 HP. Mount for the motor as base plate. Moving on to the simulations. This is our configuration 1 FPA. The attached here through threaded mounts to the lift frame. The base supports are mostly right here on all 4 sides. As you can see, as the motion is up for the lift frame, the weight of the molds take it down and then creates this tensile stress right here that eventually creates a lot of deformation in the middle of the lift frame. For our second variation, it's very similar to the first one, except the base supports are extended. It's on both sides instead of one side, and the connection is the same as the first one, as threaded. For our third variation, we use the rod clevis mounts provided by the manufacturer. Use those and have the surface area increased compared to threaded mounts. And for that, I think the deformation was a lot lower compared to the second one. For our final variation, where we use the rod that goes straight to the lift here and attaches through welding, but it's a very minimum area that's attached, so that's why we have high deformation and high stress. Next slide, I'll show you that. For the elevator system, we chose face plates that are right here. Face plates that are attached here. It creates a compressive force, which is working against the gravity It sits underneath the system right here, so when it's pulling up, it's creating compressive force down towards these plates. And as you can see, most of the stress is made on plates right here, and that's where the concern is. As for the overall deformation and stress results, the lift variation 4 is out of the contention for the design because that's the highest deformation and stress. The only elevator simulation done, which is the one we plan on using, the other 3 ones. Ultimately, it comes down to factor of safety. We had a highest factor of safety for lift variation 1, but we chose variation 3, the next design, because the first one has threaded connections as I talked about, and it is what the current hydraulic system has, and that probably creates a part in the misalignment problem. So we moved away from that and used a manufacturer-made component. It's easier to have maintenance done because we can never take the pins out.
So each of the cylinders has an absolute encoder, which allows the plant to track the cylinder's extension and applied force at any given time, which is useful for determining whether or not the cylinders are breaking down and if the lift frame or elevator is properly aligned. Additionally, there are 2 proximity sensors that alert the PLC when the cope enters the closing machine and it's ready to be picked up, and when the drag enters the closing machine and is ready to have the cope set back down.
Their final design in motion, it shows our mount for the lift and our mount for the elevator, as well as the pusher LQC. As for the timing sequence, it stays the same as our current production time cycle, which is 15 seconds, so it won't have a protection effect during production. Also, the maximum time the ACS molding machine is able to run.
So for the maintenance considerations, the cylinders have the ball screw, which is the component that's most likely to break down. There are 2 separate lifetime expectancies based off of the ball screw length. On here, the dashed line is 0.2-inch ball screw, and the solid line is 4.4-inch ball screw. The lift frame and elevator have different lifetime expectancies based off of their stroke lengths. The lift frame has a 13-inch stroke, which means it has a shorter life than the elevator that has an 11-inch stroke. So the ball screw for the cylinder will either need to be replaced every 3 weeks for the 0.2-inch ball screw or 7 weeks for the 0.4-inch ball screw. The elevator will need to be replaced every 4 weeks for the 0.2-inch or 9 weeks for the 0.4-inch. The cylinders will also have to be lubricated regularly to maintain the plant's desired level of production. The rack and pinion system gears have to be replaced every 6 weeks, and the motor will need to be lubricated regularly as well.
Summary, as stated earlier, our problem was the misalignment of the cope in the drag mode. The problem was solved by implementing my electric cylinders, and our results were validated with the software. Our design choice was version 3, and the only option performance matched for design. There was no complement to production and cycle time. And for future work, to work on a cylinder demo, ensure compatible components and installation strategy.
I have one question. When you say misalignment for their hoop and drag, what kind of defects are they facing on?
So each of the molds are made out of sand, so it's not as much of a problem for the camshafts, but they also make crankshafts. So the sand, it sticks out of the top of the mold, so on each side, and they're not set down perfectly aligned, the sand falls in, and when the iron is poured into the molds, the sand impacts the shape of the camshafts or crankshafts.
So you're saying it's an intrusion effect?
Yeah.
Because of the sand?
Mm-hmm.
Question? Yes. How did you choose the cylinder?
we started with the basis of the software that was compatible, so the Allen Bradley software, and then we looked into a lot of different types of linear actuation, and we determined that most actuators can't produce the force required. So we kind of ended up with cylinders.
In your opinion, do you believe that your only viable choices were to keep the hydraulics or to move to these ball screw electric cylinders?
I think so, just because there's not a whole lot of options of controllable systems that can produce the level of quality the plant is looking for.
Also, that deal is better. So that
So do you believe there's any disadvantages to changing from the hydraulic system to the electrically driven system?
I mean, there will be a little bit more maintenance that the cylinders will need, but it's more predictable compared to hydraulic systems because the ball screw wears out faster than a normal hydraulic system would.
So it's more frequent maintenance. Do you have any idea of the cost of maintenance?
Not at this time, no.
Any questions? I have a question. Each of you, okay, briefly. What do you learn from this talk?
I learned a lot about linear
Yeah,
actuation.
tell me something.
Just being able to utilize the skills that we learned so far. Actually, I find it's really cool.
how to isolate a certain component out of the whole system. When you really machine isolate something, I think having an idea how to isolate a
just researching different components and considering more than just cost, I guess, was very important to me to learn on this because we had to investigate the force capabilities, the controllability of each type of equipment and that. So that was interesting.